String theory explains simply why physics keeps coming back to tiny strings. Right now, string theory sits in a strange place in science. It is one of the most famous ideas in modern physics. It is also one of the hardest to prove. The basic premise is simple. It tries to connect two big rulebooks of nature that do not fit together cleanly. The physics of the very small and the physics of the very massive. The tension is that it offers a deep, elegant picture of reality, but it has not yet produced a clear, direct experimental yes or no. This piece explains what string theory is in plain language, why it was invented, and why it remains both influential and controversial. It also lays out what would need to happen for the idea to move from beautiful math to confirmed physics. The story turns on whether the smallest building blocks of nature are points or tiny vibrating strings. Key points. String theory says the most basic stuff in the universe might be tiny strings, not point-like particles. Different vibrations would show up as different particles. Its main goal is unity, one framework that can describe gravity and quantum physics at the same time. The idea naturally brings in extra dimensions beyond the three of space and one of time we experience day to day. Many versions of string theory exist, and they can describe many possible universes. That makes testing it difficult. Even without direct proof, string theory has shaped modern theoretical physics, especially ideas about black holes and spacetime. The central challenge is practical, finding a distinctive prediction that real-world experiments can actually measure. Background. To understand string theory, start with a simple picture of what particles usually mean. In most basic physics models, an electron is treated like a point, not a tiny ball. Just a point with properties. String theory changes that picture. It says the electron, and everything else, could be a minuscule strand of energy. Think string in the loosest sense, a one-dimensional object. It can vibrate, and those vibrations are not just decoration. They would be the thing we perceive as mass, charge, and the identity of the particle. A clean analogy is a musical string. One guitar string can play many notes. The string is the same object, but different vibration patterns sound different. In string theory, the universe's notes would be the particles we detect. So why reach for this idea at all? Because physics has two incredibly successful theories that speak different languages. One is quantum physics, which is excellent at describing atoms and particles. The other is general relativity, which is excellent at describing gravity, planets, black holes, and the shape of spacetime. Each works brilliantly in its own domain. The trouble comes when you need both at once, like near the center of a black hole, or in the earliest moments after the Big Bang. In those extremes, the theories clash. String theory is one attempt to build a single framework that includes both. In its best-case story, gravity is not bolted on. It falls out of the math as one of the string's vibration patterns. The extra dimensions are another headline feature. String theory typically needs more dimensions than the four we experience. The usual explanation is that extra dimensions could be curled up at scales too small to notice. Like an ant walking on a cable that looks like a line from far away but is a tube up close. This is where the idea becomes both exciting and slippery. The math can be rich enough to describe many possible hidden shapes for those extra dimensions, many possible vacua, and many possible low-energy outcomes. That flexibility can look like strength. It can also look like a problem. Analysis, political and geopolitical dimensions. Big ideas in physics do not live in a vacuum. Research communities do. Funding does. National priorities do. String theory became dominant in some parts of theoretical physics, partly because it offered a shared language for difficult problems. If you want to attract talent, publish influential work, and build prestige, a unifying framework is a powerful magnet. That influence has a downside. When a field leans heavily into one approach, it can crowd out alternatives. Critics worry about intellectual monoculture, too many careers tied to one toolset. Too few incentives to explore radically different ideas about quantum gravity. There is also an international dimension. Fundamental physics is global, but resources are not evenly distributed. Different countries and institutions place different weights on pure theory versus experiment first. In places where experimental access is limited, advanced theory can be a practical way to compete. In places that run major experimental facilities, the pressure to connect theory to measurements is often sharper. Economic and market impact. String theory does not move markets in the obvious way that a new battery chemistry might. Its economic impact is mostly indirect. But indirect does not mean nothing. First, it trains people in high-level mathematics, modeling, and problem-solving. Many of those skills migrate into technology, finance, and engineering. Second, the mathematical techniques developed in theoretical physics can spill into other fields over time, sometimes in surprising ways. Third, the long arc of basic research has a habit of paying off later, even when the original motivation was abstract. The counterpoint is fair, opportunity cost is real. Time, funding, and talent are limited. If an approach cannot be tested for decades, policymakers and funders will ask whether the balance is right, especially when applied research can show clearer near-term benefits. Social and cultural fallout. String theory became famous beyond physics because it sounds like a final answer. Everything is strings. It has a clean hook and a grand ambition. That makes it a magnet for popular explanations, documentaries, and debates. But public storytelling can distort what the science actually is. String theory is not a single neat package with one confirmed set of predictions. It is a large family of ideas and methods. The phrase theory of everything can also mislead. In everyday speech, theory can sound like a guess. In physics, it usually means a structured framework that explains known facts and makes testable predictions. String theory is complicated because it is strong on structure and ambition, but weak on direct tests so far. That gap creates cultural whiplash. Some audiences hear unification and assume victory. Others hear hard to test and assume it is nonsense. The reality is more nuanced and more human. It is a serious attempt to solve a real problem, with real achievements and real unresolved questions, technological and security implications. String theory is not a weapons program. It is not a surveillance tool. Its security angle is more subtle. It has influenced the way physicists and mathematicians think about information, space-time, and the limits of measurement. One example is the idea that space-time and gravity might relate to information in deep ways. Even if string theory itself is not confirmed, some of the tools and concepts developed around it have shaped modern conversations about black holes, entropy, and the fate of information. Those themes overlap with the broader rise of quantum information science. The honest limitation is this: none of that means string theory will directly produce a new gadget you can buy. The technological story is about long-term intellectual infrastructure, not near-term product pipelines. What most coverage misses. Most coverage treats string theory like a single bet. Either it is right or it is wrong. A more accurate picture is that it is also a toolkit. Some results inspired by string theory have been useful even outside the strict goal of proving strings are real. That matters because science does not always progress in a straight line toward one final model. Another overlooked point is that the hardest part is not writing down a beautiful framework. It is carving out a prediction that cannot be easily mimicked by other theories. A theory that can explain many outcomes can feel powerful. But for experimental science, power without distinctiveness is a trap. The real prize is a signature, a pattern in nature that only this kind of theory would naturally produce. Finally, there is a psychological factor. Humans love elegant stories. Physics is full of them, but nature is not obligated to be elegant in the way humans prefer. The tension inside string theory is partly a tension inside us, our desire for unity versus the universe's right to be messy. Why this matters? In the short term, string theory matters because it shapes what many top researchers work on, what graduate students train in, and what kinds of questions get asked about black holes and the early universe. In the long term, it matters because the quantum gravity problem is not going away. Any society that invests in deep science is, in a sense, investing in a better map of reality. That map eventually informs everything from cosmology to materials science, even if the route is indirect. Who is most affected? Researchers, universities, and science agencies first, but also industries that hire quantitatively trained talent, and education, systems that translate frontier ideas into the next generation's curriculum. What should observers watch next? Not a single string theory test on a calendar, because no decisive one is currently guaranteed. Instead, watch the broader hunt for quantum gravity clues, tighter measurements of cosmic signals from the early universe, better observations of black holes and gravitational waves, and any new particle physics results that force theorists to update their assumptions. If string theory ever gets a clean experimental handle, it will likely come through one of those channels. Real-world impact. A graduate student in California has to choose a research direction. String theory offers powerful math and prestige, but also uncertainty about whether the work will connect to data in their career lifetime. The choice is not just intellectual. It is about job prospects and identity. A science teacher in Manchester wants to explain modern physics without overselling it. They face a tightrope, keep the wonder, avoid the hype, and show students that we don't know yet is a normal and honest part of science. A software engineer in Bengaluru loves physics and follows it like a sport. String theory becomes a way into big questions, even if it never becomes testable. For them, the value is inspiration, not proof. A research funder in Washington has to justify budgets under pressure. They must balance near-term deliverables with long-term discovery. String theory becomes a case study in how societies decide what worth it means when outcomes are uncertain. Conclusion. String theory is simple to state and hard to settle. It says the smallest ingredients of reality might be tiny vibrating strings, and that this could unify quantum physics and gravity in one framework. That ambition explains its lasting pull, but the fork in the road is clear. Either string theory, or something like it, will connect to a distinctive experimental signature, or it will remain a beautiful and influential structure that helped physics think better, without becoming the final description of nature. The signs to watch are not slogans. They are constraints, new measurements that pin down the early universe more tightly, new insights about black holes that demand a specific quantum gravity explanation, new particle physics surprises that narrow the range of viable theories. That is how the story will start to break one way or the other.